So you're taking this course and you're probably wondering to yourselves, what is geology? What is the science of geology? And geology is commonly confused with several other related sciences, not always, but sometimes it is confused with related sciences such as anthropology, archaeology, and geography. Anthropology is a study of the evolution and history of humans and their ancestors. Archaeology, which is a closely related field to anthropology, studies the history of human civilization, tools, art, etc. over the millennia. Geography, on the other hand, studies the surface, land features, people, natural phenomenon such as weather, and is confined mostly to the surface of the earth. And many people know that geography is the science that produces maps, although it's much broader than that. In contrast, geology, think of it as a whole earth study. We study everything from the upper atmosphere. We also study Earth-like planets and other planets that circle the suns. We're interested in that. But more importantly, we study the solid Earth, including the rocks, minerals, and physical structures that compose the Earth, as well as the dynamic processes that shape it over geologic time. The Earth is 4.5 billion years old, and geologists toss that number around as if it were nothing, and we get kind of used to it. We don't really think about what is 4.5 billion of something, and I would love to have $4.5 billion. I can't imagine what $4.5 billion would be like. So it's also hard to imagine what 4.5 billion years of time are like when our lifespans are on the order of, say, 80 to 100 years at most. So we're talking about a very, very short period of time in our lifetimes compared to the age of the Earth. So how do we decipher this? How do we figure out the age of the Earth? And there's a saying, an old adage in geology that says no dates, no rates. What that means is that if we cannot determine the absolute age of something or even the relative age of something, then we cannot determine any rates of evolutionary events. We can't figure out the rates of ancient processes. So the key to geology and the key to solving geologic time is to come up with some measure of absolute or even at minimum relative rates of geologic time. And we've done this. And we produce what's called a geologic time scale, and it's almost always shown as something like this, a spiral. Sometimes it's shown as a column, but you can see it starts here with the modern era and kind of this one kind of swirls back through time to 4.5 billion years ago. And what's interesting about this, and it's interesting about every geologic time scale, almost every geologic time scale that you look at, is that this first 540, 538 million years is always shown much bigger as compared to the 4 billion years that preceded it. And the reason for that is simple. We know much more about what happened in the most recent 538, let's say 550 million years, more so than we do about the previous 4 billion years. Yet we're learning more and more about it. So properly scaled, of course, this would be very small, and this tail end that kind of spirals down into nothing would be much, much, much longer. So then the question becomes, well, uh, how did we determine the age of rocks? How do we determine that? And the geologic time scale is divided up unevenly into different intervals of time. When we think about the human calendar, we think about that the year is broken up into 24-hour days, the hours are broken up into 60 minutes, and the minutes are broken up into 60 seconds. So we have these divisions of time. Geologists do the same thing, although the divisions of time are more unevenly spaced. And we start with the big ones, the big intervals of geologic time, and those are called the Hadean, the Archean, the Proterozoic, and the Phanerozoic. The Phanerozoic is all modern life. It's that last 550 million years. The Proterozoic means early life, and these are when life forms were quite simple. Archean is ancient, and Hadean is just like it sounds. It's a time interval on Earth when the entire planet was likely molten, hence like Hades or hell. Those major intervals of geologic time, and we'll just go through the Phanerozoic. So the Phanerozoic is broken down into three eras called the Paleozoic, Old Life, the Mesozoic, which is Middle Life, and the Cenozoic, which is Newer Life. Within those eras, the Paleozoic is made up of the Ediacaran, Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, and Permian. The Mesozoic is made up of the Triassic, Jurassic, and Cretaceous, and the Cenozoic is made up of the Paleogene and Neogene. And then even those are broken down further into epochs and stages. And we're not going to ask you to know that. If you take historical geology, we'll eventually make you learn this geologic time scale so you can be more familiar with what intervals and eras that we're talking about. But the question is, how did science arrive at 4.5 billion years? So I'm going to go through a brief history of the age determination of the Earth. Early philosophers, very early philosophers, not necessarily scientists, thought that the Earth was eternal. It had no beginning, it had no end. It was just always there. And I think humans have always been interested in questions like these, at least when humans started asking questions. How old is the Earth? Because we know our lifetime and we see the progress of our lifetime. And so it's common to wonder, well, what is the lifetime of another organism? And what is the lifetime of a tree? What is the lifetime of the planet that we live on? So it's a curiosity, a natural curiosity that humans have. And the first quantitative attempt, the first really quantitative attempt where someone said, hey, let's try to figure this out. And it happened to be Archbishop Usher in the 1600s. And what he did was to read the Bible, the book of Numbers specifically, where if you read that, you know, it talks about so and so begot so and so who begot so and so, and it goes back. Then you go even earlier to Genesis and Adam and Eve. And so Usher said, okay, if we take all those generations discussed in the Bible, then you come up with about 6,000 years. So he determined the age of the Earth was 6,000 years. Now that was scholarly work. I say not scientific, but in some ways it was good science for the time. He actually said, okay, let's look at what information I have and let's try to calculate the age of the Earth. He later determined an exact date of October 23rd, 4004 BC at precisely 9 a.m. So very, very accurate age determination. If you go back 4004 BC, in 1996, that was the true 6,000 year birthday of the Earth, and they had a big celebration in London, which is where Archbishop Usher was from. So this was the first real quantitative attempt to try to establish the age of the Earth. And it actually hung around for a long time. And part of the reason, of course, is that there were some other observations that were made or stories in the Bible, including Noah's flood. And so Noah's flood, of course, talks about all these animals being killed in a flood, including humans that were killed in a flood. And the rock record contains lots of dead animals, right? So it seemed to make sense. In fact, one fossil that was found here was named Homo diluvii testis, which is Latin for man who witnessed the flood. So here's a case of a scientist looking at a fossil, assuming that there was a flood, and then looking at this fossil and saying, oh, here it is. Here is a fossil of a man who witnessed the flood. And it actually turned out to be a giant salamander, not human at all. So the Usherian estimate held sway. And in fact, you can look in Shakespeare, and I can't remember the exact play, but there is something in there that says at the beginning, and lo, the Earth is but 6,000 years. So during the 17 and 1800s, most naturalists, most people who were studying the Earth were also clergy, And so they kind of stuck with that 6,000-year-old Earth until they started looking at the evidence. So instead of looking through the literature to try to find out the age of the Earth, they actually went outside, started looking at the rocks. And they quickly realized that there was something wrong with Usher's estimate. And they also realized that there was no evidence of any global floods such as Noah's, and they concluded it was most likely a borrowed myth from the Sumerian epic of Gilgamesh. And there are some commonalities. If you've taken, ancient history, you realize that Noah and Gilgamesh, um, the Sumers and the Hebrews were closely related cultures, so they probably shared oral traditions, they probably shared stories. And both narratives involve divine beings sending a flood to wipe out humanity. There is a single family or individual that's chosen to survive and to preserve all life. Both involve the use of birds to determine when land has reappeared. And both serve as foundational cultural myths explaining humanity's place in the world and divine human relationships. Now, as I mentioned, it was logical to assume that it was a global flood that left all these fossils. Unfortunately, and this was quickly realized, and if you've been in a flood, you know this, floods are chaotic. They don't produce order, they produce a lot of disorder and tend to create a mess. And naturalists who studied the fossil record realized that it contained an orderly sequence of life that was completely at odds with the notion of a global flood. You could correlate fossils from one continent to another, and you would see the same fossils in the same order on one continent as you would see on another continent, completely anathema to the idea of a global flood. So that quickly took a back seat to the idea of a 6,000-year-old. Didn't make sense. There was other evidence, and scientists actually started looking at rocks and trying to figure out how are these rocks formed, what order are they deposited, and what can we learn from that. And there were three relatively simple principles that Nicholas Steno came up with. And one is original horizontality, and that's simply that sedimentary rocks are laid down in horizontal layers with the oldest rocks on the bottom and the youngest rocks on top. That leads to the second law or principle of geology, superposition. Younger rocks sit on top of older rocks. And the last one is cross-cutting relationships. And I show a cross-cutting relationship here. And a cross-cutting relationship just simply means that a rock that cuts through another rock, like this black rock here, it's called a mafic dike. This cuts through this lighter colored rock, and therefore the darker rock is younger than the rock that it cuts. And that's called a cross-cutting relationship. We don't know how much younger, we just know this black rock is younger than the lighter rocks. So we can look at these in a picture. Here's the law of superposition. The oldest here on the bottom, the youngest on the top, and the order would be 1, then 2, then 3, then 4. There's also a law of lateral continuity, and that means if there's an erosional feature here that cuts through, we can imagine that 4 originally cut all the way through this layer and has since been eroded. We also know that if we see that rocks have been folded, such as this, they still maintain that same sequence of events with the oldest on the bottom and the youngest on the top. And then the cross-cutting relationship, as I showed you before, we have 1, 2, 3, and 5. And notice that 4 cuts through 1, 4 cuts through 2, 4 cuts through 3, but does not cut through 5. So the order of events here is 1, 2, 3, 4, 5. And in your lab, you'll be doing some practice with these basic principles. So these don't give us absolute age, right? We don't know that one could be 100 million years old and 4 could be 99 million years old, or 1 could be 100 million years old and 4 could be 50 million years old. We don't know. We don't know the age difference between these. We only know that there has been some time passed. So this is called relative dating. We just know that 4 is younger than 1, 2, and 3, but we don't know by how much. Now, another famous geologist that came along was Hutton. And Hutton was an interesting character. He was a very careful observer of processes on Earth, and he was a horrible, horrible writer. In fact, if you try to read Hutton's book, good luck. It's very, very hard to understand. But Hutton went out and watched things like sand being deposited and realized that it would take a long time to build up a layer of sandstone such as the ones that he saw in Scotland. And as he watched these sands being deposited by rivers or other things that he observed, he realized that by looking at modern processes, that ancient processes could be explained by using modern analogs. So a sandstone that was a billion years old and had the same features as the sandstone as he saw in Scotland, he realized that that sandstone was likely deposited in the same sort of environment. And so he called that uniformitarianism, that the processes that we see operating today can be used to interpret the past. Very important concept. Another one, Charles Lyell, who is considered to be the father of modern geology, he looked at a lot of things. He wrote the first textbook on geology, which was used up until the 1930s. And Charles Lyell, in particular, one of the things he looked at was the evolution of marine mollusks in Cenozoic, those recent sediments. And he guessed that the Earth was about 80 million years old based on that. And that's actually not too bad, because the current estimate is that the Cenozoic is about 65 million years, the beginning of the Cenozoic. What's important is that Lyell, like Charles Darwin, who looked at the evolution of animals, viewed geology as deep time. They saw the Earth as having a very, very long history of time rather than some short interval of time. And there were a number of other people who tried to figure out absolute age determinations for the Earth, and they had clever ways of doing that. One of my favorite was Comte de Buffon. He noted, number one, he noted the similarity between humans and apes about 100 years before Darwin. He didn't write it up as an evolutionary process. He just said, hey, you know what? We don't look too dissimilar from apes. And he questioned the idea of a 6,000-year-old Earth. And he said, hey, I make cannonballs. The Earth, we can just imagine that the Earth was formed just like we form cannonballs. It was formed as a hot molten iron ball and has cooled down. So what he did is he manufactured cannonballs of different sizes and measured how long it took them to cool from a molten state to a solid state, and then extrapolated that up to the size of the Earth. And he arrived at an age of about 89,000 years for the Earth. Again, not 4.5 billion, but also not 6,000, much longer than 6,000. There was also an Irish scientist named James Joly in the 1800s. Also a very clever experiment when you think about it. He knew that rivers delivered elements into the ocean, such as sodium and chlorine. And he said, all right, well, here's a river. He measured a few rivers and he measured how much the salt content was in the rivers and then the salt content in the ocean. And he said, well, if we have this much water being delivered into the ocean with this much salt, how long would it take the oceans to get as salty as they are today? And his estimate was that the Earth was more than 90 million years old. So again, much, much longer than that. 6,000, still far shorter than the 4.5 billion years that we think today. Interestingly, Joly worked with a physicist named Rutherford, who we're going to meet shortly. Perhaps the most influential scientist of the 1800s was a man by the name of William Thomson, or Lord Kelvin as he was more commonly known. And Lord Kelvin was an interesting character. He was the Einstein of the 1800s. He was the Stephen Hawking. He was just a brilliant man. And when Lord Kelvin said something, people listened, scientists listened. He was a contemporary of Darwin, but more importantly, Lord Kelvin was not a big fan of Darwin. He did not like the idea of evolution. He thought it was both culturally and spiritually flawed, so he really hated Darwin. Yet he knew that Darwin needed a lot of time if if Darwin's ideas were correct. An older Earth was an absolute requirement of Darwin, and Darwin required more than 100 million years for the age of the Earth. So, what did Lord Kelvin do? Well, he calculated the age of the Earth based on the time that it took for the Earth to cool from a molten start. His estimate was based on experimental evidence. It was very precise and very mathematical. And he came up with an age of about 20 million years. How did he do this? Well, he went into mines around England, coal mines, and measured the increase in temperature with depth. And then from that increased temperature with depth, he made some assumptions about the initial uh, heat that was in the earth and how long it would take to cool from a molten state. And I don't know why I did that, but I like it. Lord Kelvin's estimate was the age of the for the age of the earth held sway with much of the scientific community. It was very hard to debate. And Charles Darwin and Joly were notable scientists who thought that Kelvin had made a mistake, but they could not figure out how. And Darwin, in particular, thought the Earth must be very, very much older than even Joly or Kelvin, and probably on the order of billions of years, not millions of years. Well, this is Lord Kelvin's mathematics. It looks maybe a little bit intimidating, but it's relatively simple. And the top of the equation here is just the assumed temperature difference between the past when the Earth formed and the present day temperature. And then on the bottom, this geothermal gradient, remember he went into these mines and he measured the increase of temperature with depth. That's what the geothermal gradient is. That's the increase in temperature with depth. And then thermal diffusivity, just think of that as how quickly heat moves through rock. And so he came up with his equation and he made several calculations and they varied between 20 to 100 million years. He kind of settled on 20 million because he knew that Darwin wouldn't have any way to refute that. But indeed, as both Joly and other scientists and Darwin uh, thought, Kelvin had made a mistake, but it wasn't really Kelvin's fault because in the late 1800s there was a discovery that was made that would topple Lord Kelvin's estimate. And one of Kelvin's students, by the name of Perry, tried in vain to convince Kelvin that he made an error, um, but Kelvin would not admit that he had made an error. And what was that discovery? Well, that discovery was radioactivity. And there were three French scientists who got the Nobel Prize for the discovery of radioactivity, and you probably know at least one of them, and that was Marie Curie. It was her husband Pierre Curie, and the third one, the forgotten one, Henri Becquerel. So those three, they won the Nobel Prize. This is when PowerPoint first came out with animation, text. So why was this important? Well, radioactive decay gives off heat. And because radioactivity gives off heat, that meant that Lord Kelvin's estimate was wrong. And I'm going to give you a little thought experiment to show you why Lord Kelvin's estimate was small. Suppose that you're taking this class now and I said, okay, here's the deal. I know that this class is a lot of work and I know you want to get an A, so I'm going to make a deal with you. I'm going to let you design an experiment where you have to tell me, based on your experiment, I'm going to have a pot of water in a room and everything's going to be held at the same, conditions. And you're going to have to determine how long ago that pot of water was boiling. Okay, so you might come in and you say, okay, well, that's pretty easy to do. What I'm going to do is I'm going to boil a pot of water in that room and I'm going to measure the temperature of that water as it cools every 20 seconds. And I'm going to make a graph of temperature versus time. And then tomorrow, when I have to take this little test, I'm going to come in, I'm going to measure the temperature of water, and I'm just going to compare it to my graph, and I'm going to say that water was boiling 3 minutes ago. And of course, I don't want to give an A in this class, not that easy. So unbeknownst to you, what I do is I put the pot of water, but underneath I have a little heater that just keeps that water hot. So it keeps it warm. So when you come in and measure that, even though I have boiled it, say 10 minutes ago, you're going to compare that temperature to your graph and you're going to come up with a time that's too short. You might say, oh, well, that was only boiled 2 minutes ago, when in fact it had been boiled, 10 minutes ago, but because I kept the heat on low, you got the wrong answer. And in fact, that's what happened with radioactive decay. Radioactive heat continued to give off heat, and Lord Kelvin was wrong because the Earth had that slow burner on the inside. So Lord Kelvin didn't know about radioactivity because it was not discovered until after he made his initial estimates. He did learn of it before his death in 1907. Ernst Rutherford, who was another physicist, actually was the clever one because he realized two things. Number one, he realized why Lord Kelvin had made his mistake. And number two, he figured out that there was a rate of radioactive decay which could be used as a clock to figure out the absolute age of materials on Earth. And he gave a talk in front of Lord Kelvin, and you can read this. You can pause this and read this. And Rutherford was a bit of a clown. He was a typical arrogant physicist, and some say that Sheldon Cooper was a character based on Ernst Rutherford and also Richard Feynman. You see, Richard Feynman was a Caltech physicist who played the bongos. And these quotes may sound very much like Sheldon Cooper. If you can't explain physics to your barmaid, it's probably not very good physics. And physics is the only real science. The rest are just stamp collecting. So Rutherford was a bit of a clown, but he was also a very, very good scientist who developed the machine by which we could measure the amount of radioactive mineral left in rocks and then determine. So the importance of radioactive decay in age of Earth determinations, because of these radioactive elements, they give off heat, yes, but they also occur for each different isotope of a certain element. It occurs at a constant rate. That rate of decay for radioactive elements is known as their half-life. Because that rate is constant, radioactive decay provides geologists with a natural clock, and that natural clock has allowed us to determine the age of the Earth to be about 4.5 billion years, and also allows us to determine dates for other rocks. And because we have dates, we can now determine rates.